Welcome to the Deep Dive. Today we're venturing into a really fascinating new frontier in AI. It's a brand new way to classify data.
Yeah, it's pretty exciting stuff.
We've got the research paper right here, Polymorphic Graph Classifier Part 1. It's from April 2025 by Alexander Baikiev.
hmm
And it introduces this, well, really compelling idea using a computational graphs that sort of build themselves dynamically.
Inspired by biology, by how our brains seem to work.
Exactly, to understand information. So our mission on this deep dive,
Get to the heart of these things.
yeah, get to the heart of these polymorphic graph classifiers, PGCs they're called, and figure out why this fresh perspective might be a real game changer.
In the core insight, you mentioned it, is that they're not rigidly programmed.
Right.
They learn by dynamically, rewiring themselves. Potentially more intuitive, more adaptable AI.
That's a great way to put it. It really seems like a fundamental shift.
It is, away from those fixed, predetermined architectures we usually see in machine learning. PGCs, or PNNs, sometimes polymorphic neural networks, they're all about flexible, evolving structures. It's actually part of a bigger idea, polymorphic graph computing.
Where the models themselves can change shape as they learn.
Precisely.
Okay, so the paper kicks off with something pretty intriguing.
The MNIST results.
Yeah. It suggests that even remarkably simple PGC setups can get surprisingly good results, sometimes even beating more complex traditional networks on, those classic MNIST handwritten digits.
Which definitely makes you pause and think.
Right. What's the magic ingredient here? What makes this self-adjusting thing work so well?
Well, a big part of the motivation, according to the paper, is tackling the known challenges with current deep learning.
Like the opaqueness.
Exactly, the opaqueness. It's just hard to understand how these complex networks reach their conclusions. Tracing the decision-making can be incredibly difficult.
They really do feel like black boxes sometimes. Data goes in, answer comes out.
And the middle's a mystery.
Yeah.
And as models get more complex, these worries about interpretability, understanding the why, and ultimately whether we can trust these systems, they just keep growing.
So PGCs are trying to tackle that head on.
That's the aim. More transparent, adaptable, flexible, and taking cues, like we said, from biology, from self-organizing systems.
Okay, so how does it work structurally? What are the building blocks of a PGC?
The paper breaks it down pretty clearly. You've
Yeah.
got the overall model, the PGC unit.
Right.
Then, importantly, there's the input routing block. Think of it like the on-ramp for your data.
Okay.
Takes the raw input, maps it into this thing called an embedding space.
Which is like giving it coordinates in a way, where similar things are close together.
Exactly that.
Yeah.
And crucially, it figures out a starting point within the main processing area, the PGC core. It uses a linear transformation for this, a mathematical operation.
Got it. So data gets its starting position and then enters the PGC core. What's happening inside there?
The core, or PGC core, that's really where the action is. It's described as an n-dimensional indexed array of PGC cells or core blocks.
Like a grid or...
Kind of, yeah. Like a multidimensional grid where each point, each cell can do its own processing and direct traffic.
Okay.
Inside each cell, there are a couple of key subblocks. First, the processor subblock. This does the actual data crunching, the transformation, right? Using linear transformations math to reshape the data and nonlinear activation functions, like ReLU, which you see in regular NNs too.
Uh-huh.
And there's a neat trick. The output is normalized and added back to the input. Helps prevent that vanishing gradient problem.
Ah, right, where the learning signal gets too weak. So this keeps the information flowing strongly within the core.
That seems to be the idea. Then, the really critical part inside the cell, the router subblock.
The traffic controller.
Perfect analogy. It takes the processed data and, using parameters the network learns, plus a decision function called argmax, it figures out the best next cell to send the data and control to.
Ah, so that's where the dynamic graph part comes in. It's deciding the path on the fly.
Exactly. That's the heart of the dynamic structure.
Yeah.
And the paper mentions an optional actuator subblock, too, for maybe more complex stuff like memory interaction, but the basic unit doesn't detail it much.
Okay, so we have these interconnected cells in the core. Each has a processor for changing the data and a router deciding where it goes next. And moving between cells is called a jump.
Precisely. A jump.
And if it goes back to a cell it's already visited.
That's a computational loop.
Okay.
And the whole sequence of cells visited, tracing that flow of control. That's the computational path. That path is the dynamic graph that defines the PGC's operation for that input,
Okay, I think I'm getting it. It's less like a fixed assembly line
right?
and more like data navigating this network, this web of processing units, and the route is decided as it goes.
You got it.
So how does this dynamic movement actually result in learning? How does the PGC function to classify things?
Well, the paper highlights a few key characteristics. One is the reuse of these PGC cells. Different data points will likely end up using the same processing units.
Which could lead to specialization.
Exactly. There's a sort of competition, and cells tend to get good at handling the patterns they see often. And the whole system is expected to converge, get better at the task over time.
Makes sense.
But like many ML algorithms, it's sensitive to the learning rate, how fast it adjusts itself.
Right, standard ML sensitivity. So convergence seems logical. Similar inputs reinforce certain paths and cell specializations, but what's the actual algorithm step by step?
It starts by setting an initial address in the core, guided by that input routing block.
Okay.
Then, for a predetermined number of jumps,
Mm.
let's say 10 jumps, it iteratively figures out the next address using the current cell's router.
And at each jump.
The data state gets updated by the processor in that cell, and the algorithm keeps track of the sequence of addresses it has visited. That's the computational path.
And what's really different here, you mentioned.
Yes. Unlike traditional NNs with a fixed input layer, the paper stresses that in PGCs, any cell in the core could potentially start a computational chain. There's no single designated entry layer within the core itself.
Wow, okay. No fixed entry point inside the main engine. That sounds like a very deliberate design choice. What led them to that? Any insights mentioned?
Yeah, they talk about some crucial findings from their early work. One was that traditional networks can sometimes really distort the input data right at the beginning, in the first layers.
Which can hurt performance down the line.
Right. And interestingly, with PGCs, they found even a single PGC cell could do surprisingly well on MNIST.
Just one.
Yeah. And sometimes adding more blocks initially actually made things worse compared to simpler setups.
That is counterintuitive. Usually more layers means more power, right? Maybe
Right.
maybe too many choices early on makes it harder for the self-organization to log on to good paths quickly.
That's a great thought, and it seems to align with their reasoning. That surprising result led directly to adding that separate external input routing block.
To handle the initial mapping carefully before hitting the dynamic core.
Exactly. Preserve the initial data features, reduce that early distortion risk, and the lack of fixed start endpoints in the core itself. That was deliberate too. Encourage self-organization, let cells operate more independently while still being connected. They use this cool analogy of wormholes linking the units.
Wormholes. I like that. So, okay, we have data transformation happening, similar math to NNs with linear transforms and ReLU.
Mhm.
But the big difference is the learning mechanism. PGCs learn via self-organization without that explicit supervised backpropagation that trains most NNs.
That's the fundamental distinction, yes. Learning emerges from the dynamic routing, the competition, the specialization within the core.
Okay, let's talk about the experiments. What did they find? Any standout results?
A few interesting things. Those computational loops revisiting cells, they found those didn't hurt the learning, which is good news for stability. Also, early stopping training early to prevent it overfitting, they found that was actually bad for PGCs.
Really? Why?
Especially for generative tasks, like making text, where you want consistent output over time. Stopping early seemed to disrupt that, and the optimal number of jumps, that was found empirically by trying different numbers in these early experiments.
Makes sense. And the specific tasks? MIST.
On MIST, adding more PGC blocks definitely boosted performance compared to just one big block. Supports the idea that the network of dynamic units works better.
Okay. And the language generation? Project Gutenberg.
Yeah, that was cool. The model learned and started generating common sentence structures, showed real promise for NLP. They even tried combining multiple books, and the early results looked good, suggesting more training could really improve it.
A self-organizing learning grammar. That's pretty neat.
It really is. It's quite something that this different architecture gets promising results on tasks we know so well.
And there was an arithmetic task too, right? Addition.
Yes, a synthetic task with binary encoded decimal addition. Got really high accuracy, like 99.95% on training, 98.58% on test data.
Wow.
And the really intriguing part, for sums over 99, the model seemed to output the leading one first.
Wait, suggesting it understood carrying? Like in multi-digit addition?
It suggests something like that, yeah. A kind of emergent understanding of carrying over just from learning on the binary digit data. Pretty remarkable.
That is remarkable, an emergent property like that. So what principles do the researchers think make PGCs work so well? Why do they converge effectively?
They suggest this discretization, breaking the problem into these separate processing blocks in the core, really helps convergence. Each block can specialize.
Right.
And the fact that blocks get reused encourages competition. If a path or block isn't working well, the self-organization, driven by backpropagation through the chosen path, adjusts it more.
Ah, okay, so backprop still plays a role, but within the dynamically chosen path, not across a fixed network.
Exactly. And they stress using small learning rates to talk about navigating bifurcation points, tricky spots where learning could go wrong.
Bifurcation points.
Yeah, and they'd even question if traditional learning rate schedules are right for PGCs.
Yeah.
Maybe fixed rates with some added randomness, some jitter, might be better.
Interesting. Exploring different optimization ideas entirely. What about the model size, number of cells, number of jumps? How does that affect things?
They found even a bare-bones PGC single-cell output layer, no input router could achieve decent results.
Oh.
But adding more blocks significantly sped up accuracy improvement. A big jump with just 2 blocks, and more jumps, longer paths, generally better convergence and stability.
But slower training, presumably.
Right, that's the trade-off, more computation time.
And the paper goes into some theoretical ideas, too,
Yeah.
conjectures about what's happening.
Yes, some really interesting ones, like thinking of each PGC cell as a rotation and deformation block that learns specific data patterns.
So a path is a sequence of these transformations.
Exactly, a composition of transformations. And they think the final classification probably happens by projecting the final data state onto the class dimension.
Yeah.
And maybe the most forward-looking bit, the idea of taking existing big neural networks and breaking them down into PGC-like structures, quantizing the solution space, they call it.
To make them easier to train by making the problem more discrete.
That's the hypothesis. Could facilitate convergence.
So let's quickly summarize the potential advantages they're seeing for PGCs.
Okay. They're polymorphic graph classifiers, inherently adaptable,
Right.
potentially much higher expressiveness, maybe exponential, because of the dynamic routing and self-organization compared to fixed networks.
More representational power.
Yeah. And improved interpretability is a big hope because of the modular structure and the explicit paths, you might be able to follow the reasoning,
See why I made a decision.
hopefully.
Yeah.
Also, maybe better scalability as resources are dynamic, and potentially more robust to overfitting because of the self-organization.
Lots of potential benefits there.
The move away from fixed structures and global backprop could really unlock some things.
So, for you, the listener, wrapping this up, the key takeaway from our deep dive into polymorphic graph classifier, part 1, is that PGCs are, well, a genuinely innovative alternative to deep learning as we usually know it. By using these self-organizing, adaptable graph structures, they show real promise for hitting some of deep learning's limitations, maybe giving us more transparency, flexibility, and strong performance on all sorts of tasks. Images, language, even arithmetic.
That core idea is powerful.
Yeah.
Simple, connected units achieving complex learning through dynamic routing and self-organization.
It really is. And it leaves us with a provocative thought, doesn't it?
The bifurcation points.
Yeah, the paper mentions those bifurcation points in questioning standard learning rate approaches. Could the way PGCs navigate these critical learning stages, could it give us clues about fundamentally different ways to optimize AI?
Maybe ways that are actually closer to how biological systems learn than our current algorithms.
Exactly. It's a fascinating possibility.
Definitely something to think about.
And hey, if you're really keen to get your hands dirty with this, the researchers made their code and beta scripts public.
Which is great for reproducibility and further exploration.
Absolutely. We'll put the link in our show notes. This is clearly a really active research area, lots of open questions. It's an exciting space to watch for future AI developments.
For sure.
Thanks for joining us for this deep dive.